Hello. What I want to impress on you is two things today. And one is the similarity between a mass on a string and a mass on a surface, and also the importance of the direction of acceleration in determining the outcome of a physics problem. Okay, let's start on the first. So if I switch colors here, so with the mass on a string, we have tension pulling upwards and the force of gravity pulling downwards. Force of gravity equals mg. On a surface, we have the same force of gravity pulling downward, and instead of tension, we have a normal force pulling upward, pushing upward. Okay? And the equal and opposite force, of course, is the force, the normal force pushing downward on this surface from that mass. Now, if we look at the vector sum of those forces, we could add them up. We could say, oh yeah, here's a normal force upwards, and here is a force of gravity downward, quite a bit longer. And so we recognize, the vector sum of those forces is right here, and that's equal to, the sum of the forces is mass times acceleration. So this means this must be accelerating downward. How could that be? Well, that could be you're moving upward and you're coming to a stop, and that's when you feel relatively light, or you're just beginning to drop downward. And so in that situation, the force of gravity is what it always is on you, but the normal force is somewhat lighter, somewhat less. Okay, so let's take a look at a mass on an inclined plane. Okay? And so we have a mass here on an inclined plane. Let's stick with black here. Okay? So we have the mass on the inclined plane. And we recognize, we have the same force of gravity, and we have the same normal force, but now it's at an angle perpendicular to the surface. That's our normal force. And again, this would be the same as if we had a string tied to something and the string is at an angle. And so now we have the same force of gravity pulling down, but the normal force, or the tension if it were a string, is off at an angle. What is that angle? So if we draw a vertical, this could be like tetherball, if that's a string. It's at an angle theta. Are we sure? Sure. Look, this is a right triangle, because these are perpendicular, the normal to the surface, right? And this is a right triangle. And if we're not sure, we can just remember that physicists are extremists, and we could let this go to 0 and recognize this would go vertical and that would go to 0 too. Okay. So how do we solve this problem? How do we find out what is the acceleration of this and what is this normal force? Well, we don't have enough information yet. What's very key is to understand we need to know the direction of the acceleration. Okay, so for instance, what if this is a child on a slide and we recognize they're just accelerating downward? The acceleration is straight down. Then we say, we know that that must be the direction of the vector sum of the forces, right? So we can add these two forces. Here we go. The force of gravity is downward. Let's put it over here. And we say, here's a normal force. But wait, I've gone too far because I know that the two forces added together must be in this direction, right? So I've got to erase this, and I'm going to erase that because it's too long, and recognize that, this is the size of the normal force, and this is the resultant force, which is mass times acceleration. And I recognize this angle is theta, and this is perpendicular because the normal force is perpendicular to the direction there of acceleration. And I can find out all those values using trigonometry. But what if this isn't the direction of acceleration? What if, in fact, this is a catapult, and this surface is blasting this mass up into the air, and it's sliding down, so the direction of acceleration is actually like in this direction, right? Not quite along the normal. then you recognize, we have to do this. The force of gravity is pulling down. Okay? And the normal force must be very great in order for the force of gravity plus the normal force to give me a resultant force in this direction. And you see, of course, the normal force is huge then compared to the force of gravity, where here the normal force was actually less than the force of gravity. Let's try another scenario, a very possible scenario for your exam. And that is, we have here, we have here a banked turn. And what this is a car. This is the wheels of the car, and you're looking at the back of the car as it travels away from you. And it's going around a turn. Here's the turn, like this, okay? And here's the path of the car. So it's going in a circle like this. And so right away we recognize, this is the direction. It's horizontal. Because it's going in a circle, we have some centripetal acceleration inward. And we might remember, this is v squared over r, but we might not think of that right then. But we know that whatever the forces are, they better add to this direction because that's the direction of the acceleration. And the acceleration is the same direction as the resultant force. And so now we would say, here's the force of gravity. And the normal force, well, that's too short, right? It's better come up all the way to where the resultant force of gravity plus the normal force, is horizontal. So this is the resultant force equals mass times acceleration equals mass times v squared over r. Okay, this is your right angle because the force of gravity is vertical and the acceleration is horizontal. And this angle is the same as this angle. Prove it to yourself. How else would we use this? Let's say we're swinging our little girl by her feet. We can model her as a mass of m0. We recognize gravity pulling down and the tension along her legs. And we say, okay, so what's happening to her? Well, what if I'm spinning her in a circle like this? Like I said, like the car was going in a circle. She's spinning around me in a circle. And so we recognize that, the acceleration must be in this direction. And when I add these two forces, the tension and the force of gravity, I better get a resultant force, the sum of the forces, equal to a vector that's pointing to the left. And in fact, that's what this is doing. Because again, she is executing circular motion and the acceleration is inward. But what if there was a frisbee stuck up on a rooftop up here, and I'm flinging her around like this to try to get her up there? Well, then the acceleration would be in that direction, right? Because her circular path, let's get the circular path, would be like this, in the hopes of releasing her up here and having her land on the rooftop. Then you say, how would we add those two vectors? Well, here's the force of gravity. So how can the tension plus the force of gravity be in that direction? The tension must be much greater. The tension must be very, very big. And now the tension plus the force of gravity, the tension plus the force of gravity gives a resultant force in that direction. And so this would be the direction of the acceleration. We can see now that the tension is huge on her. How big? Well, here's the force of gravity. And so the tension on her little body, on her ankles, would be 1, 2, 3, about 4 times her weight. So would I do that to my little girl? Probably not. So, in summary, what did we show? Hopefully we learned that a mass being pulled with a tension, with a string, is the same physical problem as a mass on a surface where the normal force is there instead of the tension. And the other thing we learned is knowing or seeing the picture with the direction of the tension or the normal force and gravity is not enough. We need to ask ourselves a very important question, is what is the direction of the acceleration?